Another way that we can describe a plane, another way that we can think of a plane is that we can think of it as a span of two linearly independent vectors. So let's say we have two vectors u and v here. The span of u and v, are all the linear combinations of u and v. So I'm looking at something times u plus something times v. So let's just say I have u times s plus v times t here, where my u and v, these guys are vector. And my s and t, these guys are scalar. These guys are just a constant. I mean, not a constant, it's a number. Scalar. So, if I look at all the linear combinations of u and v, I look at the span of u and v. Well, this is going to give me a plane. In particular, if I'm looking for a plane that passes through a point Q, which is x0, y0, c0. So I have this point x0, y0, c0, and I want this plane to be parallel to two linearly independent vectors u and v. So in other words, I want the plane to be parallel to u and v, and that's kind of what you see here, because u and v belongs to the plane, so it is parallel to the plane. In other words, u and v, these two linearly independent vectors span my plane. Now, the equation for this plane is going to be, well, what else? It's going to be just, I start off at my point Q, right? And I add this Q by any linear combination of u and v. So the equation of my purple plane here is going to be just Q plus the linear combination of u and v. So this guy, Q plus Q, which is my initial point, plus my vector u times some number, plus v times t. This is going to be the equation of the plane. Notice that this is actually a vector value parametric function. It is a vector value function because, well, my s and t, my u and v, these guys are vector, and q, this is a point, but we can also kind of view it as a vector. And my s and t, I have kind of two variables here. So in a way, I have a parametric kind of equations playing along here as well. So let's now take a look at the example that we have down here. I'd like to find an equation of the plane that passes through this 3 point, 1, 2, 9, 3, 2, 7, and 1, 4, 13. So, well, it's kind of hard to draw this 3 points. So let's just say I have 3 guys. It's 1, 2, 9, and then 3, 2, 7, and then 1, 4, 13. Well, so if I have a plane that passes through this 3 point, then I can visualize it as a plane that passes through this guy 1, 2, 9, and contain these two vectors here, this guy and, well, let me use another color, and this guy. Well, I can use the same color. Let me change my mind. Okay, this guy and this guy. So I'm looking at the span of the two green vectors here. That should give me the red plane, but I also want to make sure that it passes through 1, 2, 9. So what is the two green vector here? This guy is going to be, let's see, 3 minus 1, so that's a 2. 2 minus 2, so that's a 0. And then 7 minus 9, so that's a negative 2. The other vector is going to be 1 minus 1, which is a 0. 4 minus 2, which is a 2, and 13 minus 9, which is a 4. So, the parametric equation for my red line, for my red plane, is going to be just 1, 2, 9 plus s times my first green vectors here, which is, it's going to be plus 2, 0, negative 2 times s plus the other green vector, which is 0, 2, 4 times t. Now, notice how the green vector that we have here, 2, 0, -2, I can kind of pull out the 2. So this guy is, I can actually view it as just a multiple of 1, 0, and -1. And the same with this guy, I can actually view it as a multiple of 0, 1, and 2. So I can, alternatively, I can actually also write this equation as 129 plus 1, 0, -1 times s plus 0, 1, 2 times t. Notice that these two equations is actually the same thing anyway, because my s now, my s here is just twice as big as this other guy. So this is my vector value parametric equation of the plane that I want. Now, well, let me actually show you two other ways that we can also do to obtain the equation for this line. So let's see. We knew that the two green vectors here, it lies on the plane, right? So let me kind of imagine that. Let me kind of redraw it. I have two vectors that lies on the red plane, which is the plane that I want. I have my vector here, I have my vector here, and my guy here. This is 1, 2, 9. 1, 2, and 9. Now then, one thing that we can do is that we can actually find the cross product of these two green vectors. Now recall that if I in 3 dimensions, the cross product of some two vectors is actually going to be another vector that is perpendicular to the two original vectors that we have. So then, if I compute the cross product of these two guys, it's actually going to give me this red vector here, and this red vector is going to be perpendicular to the two green vectors that we have. And so that makes this pink vector perpendicular to the red plane, and that makes this pink vector the normal vector of the red plane, and we can use that to actually find the equation of the red plane as well. So let's now compute the cross product of the two green vectors here. Let me actually just go with the reduced one, because this is going to make it a little easier to compute the cross product. So the cross product of these two guys is going to be 1, 0, -1, and then 0, 1, 2, and then I, j, k. I compute the determinant of this guy, and that is going to give me, let's see, it's going to give me I, and then my j is going to be multiplied by, let me think, my j is going to be, okay, now I lost my location. Okay, my j is going to multiply by -2 j, and then my k is going to multiply by 1. Okay, so this is the normal vector to this plane. Well, let me actually kind of make this the same color. Okay. So this is my pink vector here. So my pink vector, the coordinate of this guy is going to be just, I pull off the coefficient, that's going to be just 1, -2, and 1. In other words, I knew that the normal vector to this plane is 1, -2, and 1. And I can use this to find the equation of the plane. It is going to be just, let's see, x minus, so it's going to be just x minus x naught, x minus x naught times the first one times the first coordinate plus y minus y naught, which is y minus 2, times the second coordinate, which is -2. So let me actually change this to a minus sign, -2 plus y minus 2 plus c minus c naught, which is c minus 9, times the third coordinate, which is 1 here. This needs to equal to 0. So here, this gives me another form of the equation of this line. And this is the second way that I can find the equation of the same plane. Well, did I say line earlier? I think earlier I said line at some point, I mean plane. Now then, well, third time's the charm. So let me actually show you a third way to actually achieve this same goal. Now, I like to find an equation of the plane that goes through this 3 points, right? But I knew that the equation of a plane, the general form of it is just ax plus by plus cc equal to d. So I can actually kind of use this fact to find the value of a, b, c, and d. So I can write a system of linear equations for this. So that means I can plug in 1, 2, and 9 into my x, y, and z here. And the same with the other 2 points, and that's gonna give me 3 equations with 4 unknowns, a, b, c, and d. So let me kind of do that here. I plug in 1, 2, and 9 for x, y, z. So I'm gonna get 1a, so I get a plus 2b plus 9c equal to d. And then I plug in another point, which is 3, 2, and 7. So I'm gonna get 3a plus, 2b plus 7c equals to d. Let me actually move my d to the left-hand side. So it's gonna be minus d equal to 0. Minus d equal to 0. And then the third equation is going to be 1a. So it's going to be a plus 4b plus 13c minus d equal to 0. This is 13, by the way. So now, I have this system of equation that I would like to solve. And let me write the augmented matrix for this guy right away. So that's going to be 1, 3, 1, 2, 2, 4, 9, 7, 13. And then negative 1, negative 1, negative 1, and then all 0. Let me go ahead and write down the reduced row echelon form for this matrix, for this augmented matrix. It's going to be 1, 1, 1, and all 0. My second to last column is going to be negative 1/6. It's going to be 1/3, and another negative. Negative 1/6, 1/3, and then negative 1/6 again, and then all 0. So that means the solution to this system of equation is going to be, it's going to be 1/6 of d, and then negative 1/3 of d, and then 1/6 of d, and d. So that means the equation of this line that I'm looking for is going to be 1/6d. Wait, I don't want to use the same color. It's going to be, 1/6dx minus 1/3, 1/3 dy, and then plus 1/6d. C equals to D. Now then, if I pull the D out, I'm gonna have D times 1/6x minus 1/3 y plus 1/6c equal to D. I cancel out the D, so I'm gonna get, let me actually also multiply 6. I'm gonna get x minus 2y plus c equals to 6. So this is also another equation of the same plane that we have here. One way that we can justify having the d around is that, notice how if I actually multiply this equation by a constant, let's say if I multiply this by 2, I'm going to have 2x minus 4y plus 2c equal to 12. So this is actually also another, it's also the same equation. So this is also an equation of the same plane. Now then, so let me actually tell you, so that means this guy and this guy is actually the same equation. And not only that, Well, you might recall this is also the same plane that we actually saw in the last example. This is also the plane that we have from example 13.1. So let's now actually visualize this all together. So we have here a plane. So this blue plane, this is the pale blue plane. This is the plane that we have been looking at. This is the plane that goes through 1 to 9. And it is also perpendicular to the 1, negative 2, and 1 here. So you can kind of see, no matter which way I look at it, this blue plane is perpendicular to the black vector that we have here. Now, let me plot the other 2 points that we have. So, here is my 2 point, which is 1, 4, and 13, and 3, 2, and 7. So this 2 point also lies on the plane. The 2 vectors that we see earlier are these 2 vectors here. So you can see that the 2 orange vector, this is the vector that span the plane. This is the 2 linearly independent vector that can be used to describe the plane. Now, it's a little hard to see that the orange vector is actually perpendicular to the black vector. So let me actually kind of move this blue point to the origin temporarily. Let's see. So I'm gonna want my blue point to be 0, 0, and 0. Voila. Okay. Now, you can see how the orange vector is perpendicular to the plane. And not only that, the orange vector is also, not perpendicular. The orange vector is parallel to the plane, and the orange vector is perpendicular to the black vector here. So this corresponds to the 2 ways that we can describe a plane. We can describe a plane by the black vector, the normal vector, the orthogonal vector, or we can describe a plane by the 2 orange vectors, which is the 2 vectors that are parallel to the plane. This is the 2 vectors that span the plane. And well, if this is not crazy enough, let me actually show you something that's going to blow your mind. So, recall that we actually deal with a couple of vectors here. We actually have these 2 vectors, 1, 0, and 1. And we have this vector 0, 1, 2. And we say that this vector is what span our plane. And we also actually have this vector that is perpendicular to the plane. This is the normal vector to the plane. We have, okay, again, 1, 0, negative 1, 0, 1, 2, and 1, negative 2, and 1. We actually have seen all these vectors before, and it's actually in example 6.1. So this actually goes back to lecture 6. When we talk about the row space and the null space of a matrix, we have kind of this matrix here, and we do this and that, and we eventually find out that the basis for the row space of this matrix is 1, 0, and negative 1, and 0, and 1, and 2, and the basis for the null space of this matrix is 1, negative 2, and 1. See something here? These 2 vectors are the same vectors that we have in the example that we have just looked at. And this guy is actually also the same as the normal vector that we have just looked at. So in a way, what essentially happens here is that the row space of this vector actually spans the plane that is parallel to the plane that we have in the example just now. And this guy, which is orthogonal to the plane, is actually just the normal vector in disguise.